Hello, everyone. All right. Um, in the last lectures, we saw that we are dealing with a multi-agent network. For consensus problem, we saw that there are no external commands, and for the synchronization problem, we saw there is one external command. Today, I would like to start with a brief overview of this consensus and synchronization dynamics, and then say a few important words about what happens when you have multiple commands, multiple different types of command interacting with your multi-agent system. And I believe in the last videos, we discussed the differences between undirected versus directed graphs. And today, all the material that I will present will focus on undirected and connected graphs. Some of the results that I'm going to show can be well extended to directed graphs. Some may not. So that's not the point. I would like to discuss when you have a multi-agent system over undirected connected graphs dealing with multiple inputs. The first case is the simplest case. You have no external inputs. And I will use these six graphs, six agents over a circle graph as my benchmark candidate undirected and connected graph. And if you implement this consensus protocol over these undirected graphs, basically all agents will converge to the average of the initial conditions. This is not necessarily the case for directed graphs, if you remember our previous lectures, but for today, undirected case, if you sum them up, 4 plus minus 2, 2, 5, 3 plus 2, 5 plus 1, 6. 6 divided by 6 agents is 1. So agents converge to 1 when there is no external comment. Now I will insert one external comment. There is only one comment, which is C, is interacting with this multi-agent system over the undirected and connected graphs. Basically, agent one is the leader agent, Ki is 1 for it, and for the rest, K2, K3, all the way up to K6 are 0. Like you see in this code, this green edit stuff affects the dynamics of the agent number 1, the leader agent, and expected, this convergence right now is to 3, this C is 3. All agents, while only agent 1 knows the external comment, but still all agents synchronize their states with respect to 3 with applied command C in this synchronization dynamics case. Now, if you insert the same command to more than one agent, like in this case, K1 is 1, K5 is 1, that's why you see this x1 minus x3, x5 minus 3, C is 3, this command. Agents converge to that command faster as you compare to one agent. In this case, 2 agents are the leaders, so convergence is faster since more agents know the external command. And practically, you can generalize this. Now, in this case, 3 agents know the external command such that they converge it faster because simply more agents in the network acting like leaders. If more and more leaders in the network, then the convergence becomes faster and faster. All right, now I would like to move to multiple commands case, but I want to start with a special case. In this case, first of all, I changed the notation. We no longer have Ki notation since we are no longer deal with one type of command, but we are using another summation I sim h. For example, what this means for agent number 5 is agent number 5 is subject to command number 1 and command number 2. So this is command number 1, command number 2. C1 is 1, C2 is 5. And what this notation means for all other agents in this case, nothing, because None of the other agents, 1, 2, 3, 4, and 6 are subject to external comments, and this green term drops out. Anyway, at the beginning, I said this is a special case for the case of multiple comments. And why I say is that when you have multiple comments with respect to the standard leader-follower algorithm, we expect a behavior so-called containment, which I will illustrate in the next slides. But for now, if you are using a leader-follower type of a framework, and if you inject two different type comments to the same agent, then you still have synchronization, meaning that agent trajectories will converge C1 plus C2 divided by 2. In this case, 5 plus 1 is 6 divided by 2 is 3. Agents converge to 3. I wanted to start with this special case. You can ignore it because generally when you have multiple commands, you inject them to different agents. In this case, agent 1 is subject to C1 equals to 1. There is no green term for 2, 3, and 6, but for agent 5, it is subject to comment number 2, which is C2 equals to 5. In this case, if you think comment number 1, it's not shown here, but one of the comments is 1, the other one is 5. And this becomes now the containment problem. And in the containment problem, agents converge. The states of agent converge to the convex hull spanned by these comments. So engineeringly speaking or practically speaking, all agent trajectories will converge to somewhere between 1 and 5. This is what convex hull means. Agent states converge to values between 1 and 5 when you have multiple comments. And this has important applications. One application is the sheep herding problem. You can view these as your dogs and these as your sheep. One dog is coming from 5, the other dog is coming from 1, and your sheep converge to the convex hull between those comments and following those dogs. If those dogs will go to, let's say, 10 and 15, then these agents states will go somewhere between 10 and 15. And it is kind of, it is related to this sheep herding problem, or in general, you can relate it to the formation problem. Containment problem has such applications. If you think one more time, you have bunch of drones, you have leader drones, basically all the follower drones track the leader ones by going to their commands convex hull. And now I injected the same command C2 to agent number 3 as well. So if you compare this case with this case, now right now, this command number 2, C2 equals to 5, is more dominant in the network in the sense that, right now C2 is affecting 2 agents versus C1, which is 1 affecting 1 agent. You will see the states will tend to move towards up since you have C2 is 5 and affecting 2 agents, so it becomes dominant. So for example, green one before it was 3.8, right now 4.2-ish, or if we look at this the most bottom one, agent number 1, right now it is at 2.6. Previously it was at 2.2, or probably 2.2 is not bad. So if you inject, for example, take C2, which is 5, inject a 6, 2, so on and so forth, you will see these agents will move more towards this dominant command, which is C2 equals to 5. Likewise, if you, instead of applying, for example, to agent 3, C2, apply C1, 1, 1, and 5, then you will see agents the states will converge to a point closer to the dominant command, in that case C1, since it will be applied twice. Now, I would like to point out an important work, so-called active-passive synchronization. Well, this type of containment behavior when you have multiple agents are nice. And I already mentioned it has some applications to formation control and sheep herding problems. But generally speaking, when I try to create formations, I generally don't like, like the sheep herding problem, agents converge to the convex hull spanned by the leader comments. I want to have precise formations for each agent, like somehow I demonstrated in the previous lectures. If you compare those formations with this containment formation dynamics, this containment, you just converge to convex hull. But with actual formation design, in the previous videos, we saw that we can more precisely control which agent should be, how much close to the other agents. So we can more precisely assign formation using other methods rather than containment. So containment is not necessarily my biggest favorite, although there are some important applications. As this being said, the idea of active-passive synchronization, which has resulted from 2017 and 2020 papers, we also wrote in our group several other papers called active-passive networks. Here, I should mention passive has nothing to do with passivity theory. There is also a passivity theory in control systems. No, active means agent is sensing an external command. Passive means, in this context of these two papers, an agent has no clue about an external command. For example, the main contribution of this active-passive part is basically these blue terms appearing here. In this case, agents 1 and 5 are leaders. Within the context of those papers, I will call it active agents, meaning that they interact with an environment, basically C1 and C2 interacts with them. The remaining agents are passive in the sense that they only exchange information with each other based on this dynamics, this protocol with this blue, this integral type of term is added. By the way, this active-passive synchronization dynamics that you see here requires not only exchanging xj, but also receiving zj from the neighboring agents. We removed that assumption on this newer paper, basically, like the classical consensus and synchronization dynamics. The algorithm in this paper does not require two agents to exchange ZJ, but it is not important for today. We are introducing the basics. This algorithm is working, not very unlike the containment, meaning that we may have multiple commands, but the main idea, which I should have mentioned a couple minutes ago, I still would like to achieve synchronization, but right now synchronization is with respect to applied commands, not initial conditions, and you no longer have one type of a command. So you have C1, in this case 1, C2, in this case 5, network will converge C1 plus C2 divided by 2. Divided by 2 because C1 affecting one entity, another command affecting another entity. So two agents affected by two commands. So that's why two commands are affecting two agents. So 2 is coming from that. And C1 plus C2, there are just two commands. And as you see, 1 plus 5 divided by 2 is 3. Agents converge to 3. Now I insert command 2 also to agent 3. Right now, we are going to have C1 plus C2 plus C2. In other words, 1 plus 5 plus 5, which is 11, divided by 3. This guy is affected, this guy is affected, this guy is affected. So divide by 3, 11 divided by 3, which is like 3.6, and agents converge to that point. And last but not least, I am adding the third type of a command. Right now, agents converge to C1 plus C2 plus C2 plus C3, which is 1 plus 1 plus 1, 11 plus 9, 20, divided by 4, because C1 affects one entity, C2 affects another entity, C3 affects, while the same entity, it affects, we need to count it as the number 2 affected, number 3 affected. So this is affected. C2 affects 5, C3 affects 5, 3, and C2 affects 3. So 4. One affected agent C2 affected, C3 affected 3, and agent 3 is affected by C2. So 20 summation of C1 plus C2 plus C2 plus C3, 20 divided by 4, agents converge to 5. Again, the idea of active-passive synchronization, you have multiple commands, but you don't want containment. You want, if you throw out these blue terms, basically you will have this. You have multiple commands, agent converge to the convex hull spanned by those of the leaders. This is the containment problem. But if you use active-passive synchronization, once you add these blue terms, agents no longer converge to the convex hull. They basically precisely converge of the average of the applied commands. As this being said, this concludes today's lecture. If you have any suggestions, any points that does not make sense to you, leave a comment and I will try to answer. And thank you. See you in the next class. Take care.